Perfect. Then I go ahead and thank you very much, Mark. And I really appreciate to have the chance here today to present you some of the work that I have been doing recently. Actually, it's let's say about 10 years that more and more of my research time is dedicated to this kind of investigation of the formation of the first generation of galaxy clusters at high redshift. And I hope with this talk to just give a glimpse of the different possibly interesting direction that where the research is going, and particularly also in perspective for a number of coming facilities that will, I think, revolutionize this field quite soon. But I think speaking about cluster formation is a bit of a misnomer, because if you think in terms of the evolution of dark matter halos, and this is a classic plot from Mo and Y 20 years ago, which shows that the number density of massive halos evolve very rapidly with cosmic time, in a way that it's basically impossible from the point of view of dark matter to say there was a cluster formation time. The massive dark matter halos, they were forming all the time. But really what we mean by the formation time of clusters is about their galaxies and stellar population and baryonic content. In fact, when we look in the local universe, we see that massive clusters are dominated by old galaxies with early type morphologies. And from the archaeology and the studies of their properties, we know that their stars typically form at high redshift, at redshift beyond 2 or 3. So we want to go there and capture this early phase of the formation of galaxies that eventually ended up in a dense structure. So basically, just to summarize our group activity in the last 10 years or so, it turned out that we basically concentrated our efforts on a very small number of structures, largely 2 for many years. This CLJ 1449 redshift 2 and CLJ 1001 redshift 2.5. And a third structure has started to attract our attention recently. It's a bit farther away at redshift 2.9. So just to say that, as you can understand from this, we are not studying clusters to do cosmology. We have definitely tiny samples, although a bit larger samples than now being assembled. But the aim or our attitude towards this research is to try to understand better the nature of the structure, the connection of the structure, particularly to galaxy formation and evolution. I hope I will show you how we have plenty of opportunities to deeper understanding of galaxy formation and evolution, at least in principle, and the connection with hierarchical structure formation. Particularly for this last point and the connection to models, but in general for understanding on what you're looking at when you study high redshift cluster, a particularly important aspect is try your best to get an understanding of the hosting dark matter halo. And to this regard, I think it's important to make a distinction from the point of view of terminology that I adopt here from this work that was published a few years ago. Diner, she was a student of Simon Lilly, that were making a very clear point in the sense that from the point of view of terminology, we should call a cluster or a group something that is consistently occupying a single dark matter halo when we observe it. And instead, we should term protocluster something that is referring to a number, possibly a large number of dark matter halos, therefore an overdensity on a much larger scale. So we have been sort of concentrating on the former, which doesn't mean that the latter is not interesting. It's extremely interesting to study the very large scale structure and therefore the structurization of the universe at all scales. But it's also important to have an understanding of the terminology, and in particular, according to this definition, protocluster is not a synonymous of high redshift cluster. They're really two different kinds of beasts, and both of them, they are interesting to structure. But I try to emphasize how it's important to have an idea of the fact that you are studying objects that correspond to a single dark matter halo. So how, just to give you some example, is a picture of one of the class that we have been studying. It's a redshift 2, it's CL 1449. You can see these HST images. You see plenty of orange galaxies, they're cluster members. The ones circled, they are quiescent, but there are also a number of star-forming galaxies, and the star formation rate here is the order of 700 solar masses per year. Just to show another, the other example, going to higher redshift, this is a redshift 2.5. And here, strikingly, in all these galaxies, you can see that there are several with white contours that correspond to ALMA detection. And globally, there is of order of 3,000 solar masses per year of star formation just coming from the core of this cluster. So already from this, you understand that there is a very strong, clear evolution respect to lower redshift structures in terms of the activity also contained inside their cores. So how do we know they correspond to single dark matter halos, like the two examples I've been showing you? One important aspect is to study the surface density of galaxies and the scale of the overdensity. That is basically consistent with something, some Navarro-Franken-White modeling with some reasonable parameters. And this is what we had been testing, for instance, again, in the same two structures there, redshift 2 and 2.5, though we couldn't detect any flattening core radius here, but the overall scale of the overdensity is of order of 100 kiloparsec, which is, or a few hundred kiloparsec, which is what corresponds to massive dark matter halos. So this is not the only thing, because of course we have been trying to use Chandra through the years with deep integration to at least have some weak detections of these very distant structures. So to use the X-rays to put some meaningful constraints on the hosting dark matter halos. But also more recently, and I wanted to show, to say a few words about this result, we used ALMA and the ACA with pretty decently long integrations to also prove the SZ signal coming from, again, CL 1449 at redshift 2 to compare to the X-ray constraint on the hosting dark matter halos, and also on the constraint that you can get from the stellar mass content and surface brightness of surface density of galaxies that I just showed before. And it's quite interesting to report that from the direct measurements, which are shown here, the amplitude as a function of the UV distance, in red, these are the original measurement as function of scale for the signal at the position of the cluster. And as you can see, it's basically consistent with 0, actually marginally positive, whereas we were observing at 3 millimeter where the SZ signal is expected to be negative from the hot gas in the dense potential well, the deep potential well. And the reason being that, of course, the cluster is also full of star-forming galaxies. And the fact that we were observing with ALMA, which has excellent resolution, allows for the subtraction, the fitting and the subtraction of all these foreground positive contaminants, resulting in these white points here with arrow bars, which are the eventual measurement from the cluster atmosphere. And so we could have an overall 5 sigma detection only after subtracting the foregrounds. And this is interesting because, of course, this is only one case, but we know that star formation is widespread in high redshift structures. So this suggests that efforts like SIMOS observatories or other efforts trying to have SZ surveys of distant structures using single dish telescope, they might be hampered in doing so at substantially higher redshift because of the star formation filling that requires interferometry. But anyway, from the point of view of the SZ signal, we could interpret it in terms of model scaling relations and convert to a Hosting dark matter halo. You can see we get a number which is somewhat lower than 10 to the 14 solar masses, but quite similar to the Chandra constraints and to what we had learned from also the stellar mass content in the structure. So once you have dark matter halos, even with a small sample, one thing that you can do, and this is just to show an example of a possible science with these structures, is comparing to lambda CDM models, just to check if more or less you are observing what you were expecting. And these already, although with a tiny number of objects, is sort of returning some interesting considerations. This is from the redshift 2.5 cluster from Wang et al. And the measurement that we had for the cluster is shown as the star here. And it's comparing this figure with a catalog from Millennium simulation that was drawn for 50 times larger area than the area from which we selected the structure here. So you can see that there are a few objects with similar dark matter halo mass simulated at that redshift, so that we can say that the chance probability of observing what we observed is of order of 10%. So sort of small, but still, I mean, it cannot have any implication on the cosmology. We will need a much larger sample to see whether the massive structure that we see is consistent with the prediction. That would be a very interesting test to do. But even more striking is the difference respect to the y-axis, where our estimate of the integrated stellar mass within the virial radius is basically a large factor above even the richest dark matter halos in terms of baryon population. So this shows that there is something that doesn't match between simulation and models, and there is something interesting that we can learn on the timing of baryonic assembly in dark matter halos. And of course, another...
Emanuele, sorry to interrupt you. This is, so what you're showing is a semi-analytical model, right? It's not because, so this means that the M-star M-halo relation is completely off in the simulation, right? So while in many simulations is built to match observations, right?
Yeah, this is a semi-analytical model. So this is telling something about the recipes by which the baryon assembling is put there. So we are basically learning something that there are, well, some ways have to be found to be more efficient in conversion of baryons into stars, basically.
Emanuele, another question. Have you taken into account that both the mass that you can observe and the mass that you can simulate for galaxies could be different? So you have applied the same cut for the lower mass of the galaxies that you can observe to make this sum?
We have attempted some integration on the mass function. So there are assumptions there which bring you into, I mean, some reasonable uncertainty for the total stellar mass. Of course, we have to integrate over the profile to some extent, and also over down to, I mean, the fainted stellar mass that is included in the model. So we have attempted to do that, and it does produce some reasonable uncertainty there. But the potential still seems to be much larger than what we could account for uncertainties there. Okay, so well, I wanted to go to this other application that, of course, when you have these kind of structures, another thing that is interesting to do is to look for passivization, so quenching and morphological transformations, because we know that this is actually the place where these phenomena have to take place. And particularly, I think this plot is interesting, again, from Wang et al. 2016, which shows for three different clusters going from ratio 1.8 to 2.5, should say that the one at ratio 1.8 is also more massive than the others. But then you can see plotted the quiescent fraction as a function of the distance from the core of the structure. And I mean, again, it's a very small sample, and this needs to be better populated, but there is an interesting trend where, I mean, in this massive cluster ratio 1.8, you see that basically it's everything passive. But then you start to increase the ratio and also lower the mass, and you see a nice decrease of the quiescent fraction. And for the ratio 2.5 cluster, it starts to be comparable within the uncertainty with the field galaxy quiescent fraction. So we're seeing an interesting effect that in terms of quiescent galaxies, it seems that even in the densest structure at high redshift, you're approaching the field. So there is no more strong segregation in these terms from cluster and fields, because a lot of the cluster galaxies, they were basically forming. And in terms of morphological transformation, I think what is most one of the most interesting findings is that it seems that mergers are widespread. So there is potentially a very important role of mergers in driving assembly and morphological transformation of cluster galaxies. And this was emphasized in this paper, again for CL1449, ratio 2. We have evidences that like the ratio 2.5 cluster is very similar. And the evidences came from a couple of different directions. One is from the sort of morphology, so not only the fact that there are frequent pairs, but particularly look at these two galaxies here where the image is HST and the contours are from ALMA. And you can see that basically the ALMA is peaking in regions where there is hardly any HST emission detected, which is sort of betraying the presence of very compact and obscure dust core with a lot of star formation happening there that most likely they're driven by mergers. And the other suggestion that mergers are important comes from observation of CO from ALMA, where a large fraction of the galaxies showed quite excited CO sleds that are more representative of starburst galaxies rather than quiescent disks. So we see this kind of feature. And I could also report another evidence which is coming from the sides of the object. This, when we detect sources with ALMA, they are typically very compact that again suggest some mechanism that is increasing the density of the gas and of the star formation. So we see this widespread in the few structure that we have been studying from ratio 2 to 3. Seems really that mergers are an important channel for the evolution. And finally, another quite interesting observations that we had a few years ago led to a different kind of probe, which is basically cold gas as proved by Lyman alpha. So in 2016, it came to us as a surprise that when observing, trying to look for Lyman alpha emitters in the field again of CL1449 ratio 2, we basically found that in addition to a number of emitters in the field, in the large-scale structure, we had this surprise of a giant Lyman alpha nebula, some 100 kiloparsec wide, that was sitting basically at the center of the galaxy concentration. So we got excited for a number of reasons for this discovery. And one is that the fact that you see this diffuse Lyman alpha emission means that in this cluster, there is diffuse cold plasma, and cold, I mean, meaning typically temperatures of order of 10 to the 4 K, but it should be contrasted with the hot atmospheres in these clusters that correspond to plasma more typically at temperatures of order of 10 to the 7 Kelvin. I'm sure here in the red are weak XMM and Chandra detection. Superimposed with in the color image is the number density, the stellar mass density of galaxies. And These other contours are the Lyman alpha nebula with some wavelet smoothing. So everything is basically peaked at the same point. So the fact that the X-ray contours, they are not exactly aligned, it's simply a problem of the moderate to low signal to noise ratio of our detections, but so they're not significant. We think everything is coming from the same position. So why this is interesting? Because the coexistence of cold gas and hot gas points to instabilities that should take place, and therefore to energy that is flowing from the cold phase to the warm phase. And this is a big and interesting research area, because as people working on clusters and local cluster simulation know, basically if you just let the baryons fall into the potential wells without doing anything, you would expect that today's cluster would be more compact and luminous than what we actually observe. So people have been postulating that at redshift probably 2 and before, there should be substantial interactions between the galaxies and the hot baryons that are starting to be assembled in the deep potential well. And perhaps we are starting, there is basically hardly any observational constraint on this important phenomenon. And with this high redshift cluster information, basically we start to have some hope to constrain more quantitatively this phenomenon. And some basic calculation shows that there might be energy exchange roughly at the level expected from simulations that have been produced earlier on. And particularly from on the same topic, we recently had some deep VLA observations, again, of CL1449 redshift 2, which with a very careful reduction and cleaning and flagging of this visibility. So we could obtain this image where in the back image is again HST, but the red contours that you can see here are actually faint radio sources. And we find several in the cluster core that don't correspond to previously known galaxies. There are a couple that actually are corresponding to the ALMA sources that you might recall that they're here. So these are just justified by star formation, but there are others that don't correspond to anything. And we think that we're just seeing individual jet-like emission coming from AGNs in the structure. And if you do this assumption and compute the injected mechanical energy in the structures, we find that this contribution is actually of the same order of magnitude to what you can get from star formation rate and AGN through outflows, which is, well, not quite like in the local universe, where radio is by far thought to be the strongest feedback channel, which is preventing the X-ray gas from cooling and producing star formation rate in clusters. But still, we can see that it's still there. And another key difference with respect to the local observations is that there is not a single super bright radio source in this cluster, but there is sort of multiple plays of radioactivity that we are detecting at the low level. Although globally, when you compare this CL1449 redshift 2 with the local cluster, roughly the integrated radioluminosity to X-ray luminosity is comparable in terms of this correlation. There is a large scatter even in the local universe. So going back to the Lyman alpha nebulas, this is actually bringing to another interesting research direction, which is the possible connection to cold accretion. So when studying galaxy formation and evolution through cosmic time, it becomes clear that you find at high redshift a lot of massive galaxies, which are defining this so-called star-forming main sequence, that have gas consumption timescales of order of 1 gigayear or less, but that are thought to actually be active for substantially longer timescales. So basically, to justify the observations and the large number of star-forming galaxies, theory postulated that, or well, not quite postulated, they showed based on simulations that you can expect a very substantial amount of fueling of massive galaxies in dense halos at higher redshift. And this plot from Dekel et al. 2009 is very well known, that is showing that this dark matter halo mass versus redshift. For the massive halos, you can expect that there is a typical some transition redshift at high redshift, so that when you go beyond this redshift, or if you are lower masses, the transition is later on, so this sort of diagonal line. But you have sort of a paradigm shift from moving from a situation at high redshift where you have this cold accretion penetrating and feeding the galaxy and allowing the star formation to take place, to a situation where instead you basically shut down this fueling, and therefore the galaxies will necessarily also stop forming star at some point. So of course, this kind of scenario is fundamental for understanding or for explaining the observables in galaxy formation and evolution. But on the other hand, there is very little direct confirmation from observation. It's extremely difficult to observe gas accretion. And according to the models, what has been proposed as the best way to trace this phenomenon is observation of Lyman alpha, particularly diffuse Lyman alpha and Lyman alpha streaming from the filaments and reaching the massive dark matter halos, as a possible way to unveil this physical phenomenon. So our detection in CL 1449 would place it in a region where, according to this theory, you wouldn't expect much residual accretion yet, but still, I mean, the theory is not set in stone. I mean, this line here could be actually somewhere else. It needs to be constrained from observation. So it's something we have been asking whether it could actually be connected or not to cold accretion. Of course, one important point is that we need to have other examples to be sure that it's not a fluke and a very strange case, but that it's a persisting phenomenon. So what we have been doing in the last couple of years is using KCWI that allows to follow up Lyman alpha in the redshift range of 2 to 3, where MUSE, for example, cannot access, to observe a number of structures. And so what I'm going to show you is just images which are basically from the Lyman alpha line over the field of view of KCWI, so of order of 100 kiloparsec. So you can see here, we observed the redshift 2.5, one cluster I've been speaking about a number of times so far. And you see we detect also there a giant Lyman alpha nebula. This is another passive galaxy selected cluster from Strazzullo et al. We thought it was a redshift 2.2 from photometric redshift, but KCWI shows a giant Lyman alpha nebula at redshift 2.5, which is also consistent with the photo Z of the galaxy in the overdensity. And this is interesting, showing sort of a double core structure, which might suggest ongoing assembly of subhalos. And here is another example of a Lyman alpha image of another structure, this radio selected cluster redshift 3.1. And finally, the one I'm going to show a little bit in more detail is this other structure, a redshift 2.91, that we observed with substantially longer integration, and which allowed us to make mosaicing. So this is actually a 2x2 KCWI field. It's roughly 50 arcseconds in this direction. And as you can see, the nebula is gigantic. The full extent is of order of 300 proper kiloparsec. But particularly what retain our interest is the morphology of the nebula, because as you can see, there is a bright core in the center, and then there is this lower surface brightness network of filaments. And we think that there are at least 3 that are quite readily recognizable that connect them, the core, to the sort of outer regions in the structure. So if you look at the galaxies that are residing below the Lyman alpha nebula that define the structure, you can see that there are these 3 red galaxies. They are all massive galaxies that we think are in the clusters. So for 3 of them, we got NOEMA spectroscopy for the ones that are actively start forming, which is A, B, and C here. There is a 4th galaxy that is undetected in ALMA, even with the very deep integrations. And we think it's an already formed passive galaxy in the overdensity, although we couldn't confirm the redshift yet. But as you can see, the 4 massive galaxies in this structure, they are very nicely sort of aligned with the core of the Lyman alpha, so that the peak of the Lyman alpha is basically located at the barycenter of the center of mass defined by these 4 massive galaxies in the structure. And so this is what I was saying. So if you just look at the mass density profile defining sigma 4, basically just looking at some geometrical average of the position of the massive galaxies in the core, you see that it aligns very well to the Lyman alpha. So this is basically a confirmation that this low surface brightness feature that looks like filament, they seems to be streaming toward the center of the potential well. So this is sort of making sense in the framework that we are seeing cold accretion, because the putative filaments, they're not going anywhere, but they seem to really be converging to the center of the potential well. And we have tried our best to estimate the hosted dark matter halo of the structure, and our best estimate is something of order of 4 in 10 to the 13 solar masses. So we think this structure is consistent with the group. We would say it's starting to be moderately low mass. And this estimate comes from the stellar mass content, the integrated star formation rate. There are sort of 1,000 solar masses per year coming from the cluster galaxies, and also from a 3 sigma blind X-ray detection at the position, just putting an aperture there and counting the photons, it returns a 3 sigma detection. So it's interesting because once we have this estimate of dark matter halo mass and the redshift, we can go back to the decadal plot, and we see that we are getting really close to the dividing line as produced by theory. And in any case, with respect to the other structure that I was showing before, we are moving to the right, where we should expect the cold accretion to become more prominent. So it's interesting to go and therefore look at what simulation and modeling had predicted that the observational features of cold accretion Lyman alpha nebula how they should look like on the base of the estimated dark matter halo mass. So if you can look in these figures here, these are predictions from Rosdahl and Blaiseau, but there are other papers like Gert and others making basically pretty comparable predictions. And what is shown here is the expected extent of the nebula as a function of the virial mass of the halo. So basically for the halo mass that we have is a bit off scale, but we should be expecting a few hundred arc seconds square, and it's quite consistent with what we observed. The luminosity, again, for a few in 10 to the 13 solar mass halo should be of order of 10 to the 44 arc per second or more, and this is also what we observed. And also, the typical surface brightness, they're pretty consistent with the models, and the fact that we observed 3 filaments is also intriguing because a number of works had predicted that that should be the typical configuration for the streaming from filaments reaching a massive node in the large scale structure. There should be oftentimes 3 filaments observed. So the basic result is that there is excellent quantitative agreement with predictions. But of course, you never know if it comes by chance and whether the models are correct. So you would like to know a little bit more, to be able to say a little bit more about whether we could be observing eventually these networks of cold accretion or not. So what we could actually say is looking at the energetics and typically considering two channels, which is the integrated star formation rate and the AGN, because basically there is an expectation that if it's cold accretion, what you would expect to see is basically Lyman alpha produced by collision of the cold gas streaming in the massive halos. And whether it's collision or something else could be gauged from the possible presence of ionizing sources, because the other competing mechanism is basically photoionization from energetic photons coming either from star formation or from AGN. But the bottom line is that even if in principle there is enough star formation to power the Lyman alpha nebula, but all the star formation is in extremely obscure galaxies, so that hardly any photons seems to be penetrating and escaping from the compact dust cocoons that are enshrouding the star formation. And from the point of view of AGNs, so we could study the global spectral energy distribution. This is work from Shou and Jean that is with you at ESC. And we could use this kind of information to constrain the presence of AGN. And the bottom line is that there is no evidence of any AGN in the structure. And the upper limits, the stringent upper limits that we can put exclude that there are enough ionizing photons from AGNs that can power the nebula. So it's an interesting situation because some reasonable analysis disfavors that can be substantial channels of power in the nebula from ionization. And if it's not ionization, what is basically left is collisions. And that would be an exciting confirmation of streaming gas, possibly from accretion. And I think the other interesting aspect comes from comparative comparison to quasar nebula, and you might be aware, but there are order of 100 or perhaps a few hundreds giant Lyman alpha nebula that are basically found around any quasar. There have been major Muse results on this kind of work. But in this case, as I told you, there is basically no AGN. So this is making, and another important aspect is that we are looking at very massive halos, whereas the typical hosting halos of the quasars, they are at least a factor of 10 smaller. So from the point of view of the energetics in this massive group, redshift 3, if you compare gravity and possibly collision-driven energy source from photoionization, you have 4 order of magnitude difference in favor of gravity playing a role in the structure. And the same thing from the point of view of gas inflow and the different role of inflow versus outflows. Basically, there are 2 orders of magnitude difference. In the quasar fields, basically because of the quasars, you can expect huge flows of matter going into the circumgalactic medium coming from the quasar itself. So it's much harder to be able to say whether there is any gas coming from outside, but the situation here is reversed. And of course, all these considerations, they are sort of indirect, and you can also look at the kinematic properties of the cold gas from Lyman alpha that seems to suggest gradients in velocity from respect to the core going to the outskirts that might be consistent with cold accretion scenarios, particularly if you have a rotation of the gas as it falls into the potential well, because you wouldn't expect large acceleration of the filaments over the Villiers radius. But another aspect that one could look at is the Lyman alpha profile. Lyman alpha is a difficult transition to interpret because it's basically affected by resonance scattering, so that what you observe can be very different from what was intrinsically produced. For instance, this case taken from this paper here, from Lyman alpha emitters, where you can see this galaxy in particular has the observer spectrum in black, but the reconstructed intrinsic spectrum is this dashed red here, because you can see it's very difficult. There is absorption in the center, and there is this asymmetry here. Now, this asymmetry is interesting because although with all the complication in the interpretation, still you can use it to have an idea of whether globally in the reference frame of the structure you're observing, the gas is globally outflowing or infalling. So for the case of galaxies, most of the spectra, they have this asymmetry, with the strongest peak being redshifted. That is typical for outflows. But in this RO1001 group, or actually 2.9, for most of the Lyman alpha emitter in the cores and the other region, particularly notably, we see the reverse. So we see a much stronger blue shifted emission and a weaker red shifted emission, which globally suggests that it could be actually infall that we are observing. There is another paper in the literature that is reporting another case with a similar spectrum from another Lyman alpha nebula. So, I mean, to close this panoramic, what we conclude is that it's very hard to give a definitive answer, but it could be that this redshift 2.9 structure, we are eventually detecting a substantial contribution from cold accretion and collisionally excited Lyman alpha. That might be one of the first direct cases where we are proving this phenomenon. So of course, we would like to know a lot more. We would like to know whether the cold accretion, if it's there, if it's of the same order of magnitude as predicted by models, or perhaps less or more. And we are not still there. There are many uncertainties in the analysis, but it seems to be promising, going toward the possible confirmation of the expectations from theory. So just the last few minutes, I wanted to use to comment on a number of coming facilities that have promised to really change this field of research in the coming decade. For example, there is a project for having a new instrument at the VLT, which is the Blue Muse, that would provide fairly high resolution spectroscopy for Lyman alpha between 1.8 and 3. So unlike Muse, this would be covering much bluer, and that would be great for this project. Also because of the large field of view, much larger than KCWI, and the high efficiency. So this kind of facility is what we need at some point to pass from fairly small samples to real statistical samples. And of course, Euclid will do great things in this research area. As you know, there you have Helmut with important responsibilities in the search for high redshift structures and protoclusters. And we know already that Euclid will provide deep enough photometry to be able to select sources like the ones I've been presenting, basically over the whole sky, so that at least for sure in the deep field where there will be many dozen square degrees observed. So this is very promising that samples at some point should explode. And you want to get redshift, and particularly, I think it's interesting that there are a number of planned future facilities that will not just go there and make some redshift confirmation on the structure, but they will allow to have vast numbers of spectroscopic confirmation on large areas. So that will allow to track the large scale structure on many different scales. So to see the whole hierarchy and the connection up to the densest peaks. And of course, for this science, and particularly given the simultaneous presence of cold gas phases with hot gas phases, the availability of Athena, when we will be launched, maybe 10 or 15 years from now, it will really have the capability to revolutionize the field and the understanding of all the crucial phases of the baryons that are assembling into the early dark matter halos, plus all the inferences on the early AGN activity, which are going to be crucial. And I think finally, I also think that SKA will have a major say on this science, not only because a while ago we showed that actually clustering of faint radio sources is probably one of the most promising means to find the most active clusters groups in the distant universe, but also because the radio will provide ways to estimate star formation rates and or AGN feedback with, of course, some degeneracy among the two. And ideally, depending on how much gas there is, perhaps it could also even have the sensitivity to detect H1s from the streaming filaments. And that would be really the thing that you want to do at some point, to have a good measurement of the mass and to understand all these cold accretion problems that has proved to be so hard to attack observationally. So we got to the end. So basically, this is my summary about research on forming high redshift clusters and groups. There are structures where there is a lot of activity from many points of view, and particularly they basically always tend to show in the core this giant Lyman alpha nebula, so that you can even think of 3 families of Lyman alpha nebula, the ones that are found serendipitously, the quasar nebulas, and also the clusters nebula to some extent. And I discussed you in some details about the structure RO1001 redshift 2.9 that provides an opportunity to test theories of gas fueling and cold accretion. And of course, we have to get a lot more information to have a conclusive picture, but we are starting. And stay tuned. We are analyzing the larger sample, and we are hoping to have a first statistical work based on 8 structure comparing star formation, Lyman alpha, dark matter halo mass, and redshift, trying to see if there is any trend coming up that could clarify again the role of gas accretion, these distant structures. Okay, that's it. Thanks a lot for your attention, and I'd be happy to get questions.
Thank you very much, Emanuele. It's always weird we cannot clap or anything with this Zoom, but thank you. I think it was super interesting. I have several questions, but I don't know if the audience has some questions. Please don't be shy.
Yeah, Emanuele, what do you propose for the James Webb? How are you going to use it for this kind of observations?
Very interesting question, Nacho. So for the James Webb, maybe I will show you one bonus slide that eventually I decided not to show, but one of the things that we also measure in the structures is ICL. And actually in the 3 main structures that we have been studying, and particularly even up to redshift 2.9 with HST images that are crucially required, because you need to subtract the foreground, the object that the cluster galaxies and all the object you have.
We are not seeing the slide, Emanuele. I don't know if you wanted to share something, but you're not seeing
it. Yours. Oh, sorry.
Yeah, you stopped sharing.
Yeah, thanks. I was displaying it to myself. Yeah, this. So this is a detection of ICL in the 1 cluster redshift 2.5. We are still working also with Paolo Di Mauro and others trying to get the results out. But as I was saying, we see ICL in several of the structures we have been studying, at least all those where we have deep HST images. And the thing is that we really need JWST to infer the mass and the SED of the ICL. So to have a say on what's the most likely formation channel, but not only that, but also the mass fraction and things like that. So I think that's quite promising. We are still trying to move in that direction. We have, for the moment, we have detections in a couple of colors that are not sufficient yet to characterize what we are seeing there. Is that so the ICL that we see is fairly bluer than the red cluster galaxies. So it's either younger or it might actually even be star forming, and that would be interesting if there is a diffuse star formation in the medium. So we are getting toward that direction, and so this was one of the things that we were hoping to do with GWST. And the other thing that, well, a couple of more things that we have been proposing, but then of course we have to see how it really works, is for the redshift 2 cluster, you can actually get extremely deep star formation rate probes with MIRI, and that's another thing we would like to do. And then finally, we have tried to follow up the Lyman alpha nebula, trying to get H alpha, because the H alpha to Lyman alpha ratio diagnostic, it's extremely powerful, particularly if H alpha is very weak compared to Lyman alpha. Then you have a direct proof that it cannot be case B recombination, but it has probably to be collisions. And then if it's collisions, that you are seeing streaming gas, so you have basically detected cold accretion.
Thanks. Any other questions? You can use the chat or just. Yeah, while you think about it, maybe I can have a question. So I have, well, one easy first regarding the first thing you said about mergers being very common. So intuitively, and some people say that in these massive structures with high velocity dispersion, you shouldn't expect too many mergers, right?
Yes.
And actually,
exactly.
Nacho is here, and he finds these relic galaxies, especially in these high density environments. And one of the explanation and models also, agree that you should find objects with little interaction in these systems, while you seem to find the opposite, right? So it's something that you can comment on, or.
Yes, I mean, you're raising an excellent point on which I'm afraid I don't have well, a way to address it properly, because it remains as a question. Because indeed, typically because of the dense environments, you wouldn't expect a lot of merging activity, but then you observed and you find these things. And it's a similar situation because, in fact, also the ICL I was just speaking about is basically a witness of a lot of interactions and probably mergers, because you need to strip the stars from the objects to get the ICL. And there are a number of models that had predicted that the ICL should become pretty much insignificant beyond redshift 1, but instead we readily detect it. So, I mean, different lines of reasoning, they purport the important role of mergers, and why there is this discrepancy with theory. It's not too clear to me. And I think another particularly relevant case is this one here. Maybe I can show you the other image. There is more zoom. The one cluster redshift 2.5. So you look at the scale here. This is 5 arc seconds. So globally, the diameter of this region is something like 20 arc seconds, which is 150 kiloparsecs. So it's a very, very compact area. And we count 12 or 13 very massive galaxies of order 10 to the 11 solar mass in this very narrow region. So I guess a question is, what what's the fate going to be of the structure. We need to know the velocity dispersion better, and of course we cannot have all the information on velocity, but one reasonable expectation could be that given how it's compact, they would have to merge on a relatively short time scale. But that would then produce 7 and 10 to the 12 solar mass galaxies. Everything here is going to merge, which is not something that we observe in high enough numbers, like in fields like Cosmos. So I mean, this to me, it's also a puzzle that we see these configurations with very high densities that presumably they shouldn't be very stable on long time scale and should again produce a lot of mergers. But so I guess this is hitting a little bit the limitation of our very small samples. We will need to have more systematic samples to understand whether they are curious findings or these are really typical situations.
Manu, but do you think you are, for whatever reason, biased to compact configurations, so that you are only studying those that have higher densities in terms of number of galaxies and so forth? It could be that the reason that you are just spotting the most dense environments at those redshifts?
It could be to some extent, because beyond redshift 2, you cannot select structures directly by like X-ray observations because it's too shallow. You can only a posteriori confirm there is some weak X-ray at the expected position once you have found the structure. So the fact that you are selecting things by overdensity of various kind of things will maximize these observable, for example, respect to others. However, from the point of view of the size I was showing before, like the Navarro-Franken-White fit, we are getting fairly reasonable fit. So I mean, it doesn't seem to have anomalously peaked profiles in the core. At least we don't think there are evidences for strong bias, but there might be some bias in that direction because of selection indeed.
Thanks. I don't know if we have time for a last question. I don't know if someone wants to say something. Don't be shy. Okay, then I'll use the time. I wanted to, yeah.
I can make just a final comment.
Yes.
I understand that most of these, if not all, of these protoclusters are in the southern hemisphere, right?
No, CL1449 is +9.
Okay. Yeah, because I mean, here we have the facility of Megara that for the field of view that you are showing just here, maybe it could be of some use for you as well. So it's just to inform you about instrumentation in the northern hemisphere that could be of some use.
What is Megara? Is a narrow band filter?
No, it's an IFU as well.
Ah, okay. Yeah, I should look into that. Yeah, it could be a nice venue for collaborations.
Definitely.
Yeah, Nacho is the Cosmos field.
This one is the Cosmos field, but yeah, the other one, CL1449 is +09. But even the Cosmos field is visible from Canary Islands.
Yeah. Yeah, that's a good point.
Yeah, it's a good suggestion. I should look into that.
Yeah, so regarding that, I mean, what would you think? I think it's hard to say, but what would you think is smoking gun evidence of the accretion? At some point, we should say, okay, this is it or this is not. And do you think it's more statistics or it's more, accurate measurements that we need? Or I was wondering, is there a way to compare more systematically with theory and saying, okay, this is the likelihood that this is, this is not a cold accretion is very low or something like that? I don't know if. Yeah.
So if you read the paper we put on the archive that it's discussing the case, at the end, it even has a sort of a pessimistic remark, that in the sense that well, you basically, if you want to unveil collaccretion from Lyman alpha, you have to think in terms of contrast. Because assuming that the theory is correct and you have this collaccretion that will produce some luminosity from collision, the big uncertainty is what this luminosity is going to be. Because I show you that prediction that seems to be fairly consistent with what we observe, but it could come by chance, and it's really coming to complex baryon physics and on very small scales. You expect formation of clouds that are very compact and with high filling factor. So all these physics, and it's not really under control for the simulation, so that they are using some recipe so that what they predict for luminosity, it might be off by at least 1 order of magnitude or more. So if it's not that we are observing, then we are observing something else, and presumably stuff that is coming out from galaxies, like it could be outflows, it could be tidal ejection from mergers, and or so material brought out from the galaxy from AGNs or star formation, which would also be streaming in the hot potential well and could also produce Lyman alpha in these ways, and plus you have photoionization. So basically, it's a matter of contrast. And even if in what we think are the most favorable situation because of the high dark matter halos and the high accretion that should maximize the visibility, if even there is not cold accretion, then it eventually might be really hard to so directly demonstrate that you have accretion from Lyman alpha emission. Still, we have to have definitely conclusions. It might be that you have a lot of collisional emission and it's really streaming gas. Also constraint on the metallicity, particularly at the edge of the halo, could help, because if you find it's pretty pristine, then you can be more confident that it's accretion rather than something coming from the galaxy that should be enriched. So you have different ways, but otherwise, it might ultimately result to be too difficult to be done from Lyman alpha. And at that point, you could think of other possible ways. So people studying gas in accretion, they're starting to see some weak evidences, and that might lead to something more robust at some point. And eventually, as I was concluding, the real thing would be to detect the H1 from the filaments with the radio 21 centimeter radiation. But there is a gigantic question mark, because again, prediction, they're not so secure in terms of natural fraction. We are not sure how much H1 gas is going to be there. So, I mean, at some point we will be observing, and if we are lucky, if it's the natural phase is important, that might be a very direct way to study the gas accretion.
Okay, thank you. Okay, I think it's probably time to close this. It's been more than an hour.
Yeah, thanks everybody for your patience and
no, thank you,
attention.
Emanuele. I think it was super interesting. And yeah, so thank you again, and thank you all for attending. And yeah, hope once you will be able to visit physically once this craziness stops.
Yeah, definitely, it would be great.
Yeah.
Looking forward to that.